Hello, this is part 2 of my electromagnetic waves videos. I'm hoping to wrap everything up in this video. I'm also hoping not to repeat myself, but I can't guarantee that I won't end up mentioning something that I've already said in the first video, but I'll try not to. I've got as far as refraction, which is where the bulk of the calculations come in our exam questions. So we've already encountered refraction in our wave behavior video. So this is where we got a change in direction and a change in speed and a change in wavelength of a wave as it passes from one medium to another. So say we've got two different materials here, and this is the boundary between them. We can draw in the normal, our perpendicular line at right angles to that boundary. So if we've got some ray coming in from the top, and then say it slows down as it goes into this material at the bottom, then it slows down, it will bend towards the normal. If it had been speeding up, it would have bent away from the normal. And the good thing with all of these rays is they're all reversible. So we can see the same. If the arrows were going in the other direction and we were coming in from the bottom here, and then we were going to speed up, then we'd be moving away from the normal if the arrows were pointing in the opposite direction. So all of these ray diagrams we can draw with the arrows either way round. It won't make any difference. So how do we quantify all of this mathematically and actually do some calculations? Right, well, there's a few things we want to put in. So we want to put in our angles from the normal. So let's go θ1, θ2. Sometimes you'll see these as a θi for incident and a θr for refracted or something like that. It doesn't really matter. So we got those, and then we want to put in refractive index. So let's call those N1 and N2. Now, refractive index is a way of quantifying the change in speed of the ray, of the electromagnetic wave in that particular medium. So a refractive index is the speed of light, so that's the speed of an electromagnetic wave in a vacuum, divided by the speed in a particular medium. So if we're moving in a vacuum, then you get C over C, which is 1. So we're getting N equals 1 for a vacuum. And that is the lowest it can be. It's only going to go up from there. And this refractive index is a function of both the material and the wavelength of the electromagnetic wave. So if you take something like glass, which is something which gets picked on quite a lot, then and you want to see the difference in refractive index for red and blue for glass, then it's going to depend on exactly what type of glass you've got, but it might be something like 1.5 for red, 1.6 for blue. So blue is bending more. The bigger the difference in the refractive index here, M1 and N2, the more we're going to get bending of the light. So if we're going from 1 here to 1.6 there, blue is going to bend more towards the normal than red is. So you're getting this splitting out of the light. That's the effect that you see when you pass light through a prism. It causes problems, as we're going to come across in the optics section when we get onto that. This is the reason that we get chromatic aberration in telescopes and lenses and all these sort of things, which is something that we want to end up correcting. So we've got that definition anyway of refractive index. This is all brought together in the very well-known Snell's law, named after, I think it was a Dutch chap called Snellius. So you can see why they shortened it a little bit. And although it's interesting that it's named after him, because although he came up with Snell's law in the 1620s, I think it was, around 1621 or something like that is when he published it. But he was by no means the person who discovered this. There's good evidence that Ibn Sal in Baghdad in the latter part of the 10th century, that he actually discovered Snell's law. You've also got Thomas Harriot. He wrote down Snell's law in letters 20 years before Snell did, where he was writing letters to Kepler. But you know what it's like, names stick. There's quite often a Eurocentrism to all of this, because that's where most of the discoveries and the science was going on. There was a bigger scientific community there at the time. than there was any other place in the world. So yeah, I suppose you've got a combination of well, naturally that's how it's going to end up occurring, because that's where most of the work was being done at the time, and maybe a preference as well for naming naming laws after their own countrymen and such like. So Snell ended up with the name, whereas it could have easily been Ibn Sal, but these names stick, and it's hard to shift them, as we see with quite a lot of things. It's quite hard to shift things like conventional current. We're still blinking stuck with. We're putting all the arrows the wrong way around on all our circuit diagrams. So it's hard to change these things. Anyway, I digress with all of that. So old Snellius, he came along, observations. So he had this n1 sine theta 1 is equal to n2 sine theta 2. This is giving us the relationship between refractive index and the angle from the normal on either side of a boundary. So that's a formula that we're going to use an enormous amount for calculations. We can also derive that, which I'm going to do in a separate video, using Fermat's principle of least time. So something that Fermat and others noticed back in the day was that light, or all electromagnetic waves, they will take the path of least time from one point to another. So if you're going from here down to here, well, okay, what path are we going to take? There's loads of different paths. We're going faster in the top part because we've got this lower refractive index. So you want to spend more time in the top part because you're going quicker, but you don't want to spend so much time in the top part that the path length becomes so much greater that you're losing the advantage. It's like those questions that you see on running away from crocodiles. You've got more chance of outrunning it on the land, but eventually, you end up in the water, and well, how much water do you want to stay in and how much time do you want to spend on land? It's a similar thing. You're trying to optimize something. So you're trying to optimize it for the minimum travel time rather than just drawing a straight line from top to bottom. So yeah, that's quite easily proved using pre-university calculus, which I'll do in another video. But yeah, it's quite an interesting exercise doing that. But yeah, we've got that path of least travel time. This also leads to the idea of total internal reflection. So say we were going the other way this time, we're going from n2 to n1. We're going from slow to fast. We're going from our high refractive index to our low refractive index. So if we came in at a fairly steep angle, okay, we'd be refracting away from the normal. Yeah, okay, great, wonderful. Eventually, we're going to get to a point where we're coming into the boundary, and we're going to be at some angle, which is our critical angle, theta c, from the normal, and the refracted ray is now going to be running along at 90 degrees here. It's going to be running along the surface. So our theta 2 becomes 90 degrees. That is the critical angle, because if we go beyond that, we get no transmission of the wave into the faster medium. So everything will then be reflected, and you just get total internal reflection. Now, you always get some reflection. So even when we had that initial case of where it was coming in steeply and then refracting off away from the normal, you'd still get a bit of reflection, but you're getting more and more and more reflection as you're increasing the angle, and then you hit the critical angle, and then beyond that is just total internal reflection. That's all you're getting. You're getting no transmission across the boundary at all. So usually in the calculations that we do on this, we assume that N1 is representing a vacuum. So we stick all of this into our equation here, and we were saying, okay, well, N1 would then be 1. Sine of 90 degrees would then be 1 as well. So we're getting 1 is equal to N2, as I've got in this particular drawing, sine of theta c. So it gives us the sine theta c is 1 over n, part the formula that you get in the formula booklet. So that's another calculation that comes up quite a lot. One thing that I suppose I should mention, I don't think I said this in the last video, but to do with transmission, reflection, and all of this, we were looking at the Huygens-Fresnel principle and the way of drawing out, the wave fronts and things like that. And then when you get reflection and refraction, you're getting this change in the wavefront. This is all well and good from a classical physics point of view. There is this sort of underlying, well, why is all of this happening? I mean, what is going on with the electromagnetic wave when it's been traveling through this vacuum and then suddenly it hits a particular medium, it hits some material, and everything's changing? And as I said in the previous video, this is all getting into quantum mechanics, but there's essentially it's an epic amount of superposition is how you can think of it. So you've got this disturbance coming in, this electromagnetic disturbance. It then hits some material. This material, of course, is made of charged particles. They're going to be disturbed by the incoming wave. So the incident wave is going to disturb the electrons, the atoms or nuclei of the material in this medium that it encounters. So, and that disturbance in itself of making those move is then going to create more electromagnetic disturbances. You're also going to get phase shifts, which is going to depend upon the nature of the material, whether you're going from a high refractive index to a low refractive index or low to high. So you can get phase shifts that happen. You're going to get all of these new waves emitted, and they're going to superpose. And the combination of all of that is going to then give the resultant wave and how it's going to continue to propagate. So that's a way of getting a primitive picture of what's going on, maybe, when an electromagnetic wave is moving from one medium to another. But again, we're kind of, stuck with the fact that we can't get that far with really describing all of this until we get into modern physics and quantum mechanics. But one thing to not get stuck in your mind, because sometimes you read these things mentioned and sometimes they stick, is that you have these sort of photons coming into atoms in the new material. So you've got this wave or this photon particle coming in, and sometimes it gets described as the electrons get excited and then de-excite and release more photons, and it's that process of excitation and de-excitation that slows the wave down, the sort of absorption and re-emission. But that is not what happens. That is just not the case. So don't get that stuck in your mind, because you'll be thinking about the wrong thing here. It's more about just having these disturbances are coming in, causing more disturbances in the charged particles of the new medium, and then that producing a new set of electromagnetic waves which all then combine and interfere. So you've got that process going on rather than an absorption and re-emission. So yeah, that's a little bit there. That then determines, depending on the phase shifts and everything else that happens, as to whether something is going to refract, whether it's going to reflect. All of those things then start coming into play, and that's a function again of the medium itself, what material that we've got, and the wavelength or the frequency, whichever one you're looking at, of the electromagnetic wave that's coming in, which is why you'll get some things will reflect, such as light from a mirror, whereas an X-ray will pass through. So it's all a function of wavelength. Okay, right, there's two other things I want to mention. That's coherence and polarization, neither of which are specific to electromagnetic waves, but in pre-university physics we tend to talk about them in the context of electromagnetic waves, and I don't think at the moment, at least, that it's worth doing separate videos on them. So I'm going to talk about them here. So starting with coherence, the usual way that we talk about coherence in pre-university physics is just to say that, well, two waves are coherent if they've got a constant phase difference. Two waves coherent if constant phase difference. So that's fine, and don't move away from that in your answers in exam questions when they're asking you to define it. I just wanted to say a couple of things about it, because coherence is really broken down into spatial coherence, whether waves are coherent through in different parts of space, or temporal coherence, whether a wave is coherent through time. So it's not as simple as the explanation that we get given in pre-university physics. So temporal coherence, so this is really related to bandwidth, as in what's the range of frequency that you've got. So if you've got temporal coherence, then you're really saying that everything is the same frequency. So the frequency is constant, because otherwise we're thinking about something changing through time here. But if you had a source which wasn't just of a single frequency, it had a little bit of variation in it. You've got some wave that's coming out with that frequency. You've got another one which is just that little bit longer frequency, say just a little bit, and they're getting out of step through time. So this is time that we've got on this axis here. So they're gradually getting out of phase. So the phase difference is changing with time. So this is why when we're wanting to get a coherent source, if we're doing something like Young's double slit or something like that, then we'll be saying, okay, fine, we want to have light of the same frequency. This is our assumption that we're having, and that we'll put into our experimental assumptions when we're writing out our exam answers. So we're not getting this change in phase difference through time, because everything has got the same frequency. Right, the other type of coherence we got is spatial coherence, which is more to do with the regularity and uniformity of the wavefronts, when we draw these things out. So if we've got all of these equally spaced straight lines, then through space everything is coherent. These waves are all moving along in exactly the same way through space. What's going on up here is the same as what's going on down there, as everything's moving along. It's not like we've got, say we had the straight line, and then this is all nice and spatially coherent, and then things start lagging a little bit on one side or whatever. We're getting some kind of change. So when you start getting these irregularities in wavefront for a particular wave, then you start losing spatial coherence. So there's these two types of coherence that when you study waves in more detail at university, that you'll start making the distinction between those. So don't worry about that too much at the moment. I think it's more a case of just being aware that there's these two different types of coherence. Just stick with the usual definitions in your A-level answers, where you're talking about two waves being coherent if they've got a constant phase difference, and that means that we're going to want the same frequency for two different waves. We don't really consider any situations where the wavefront is changing. Spatial coherence is pretty much just overlooked. It's just taken as a given, really, in our A-level scenarios. Right, so that's coherence. The other thing I want to talk about, right, polarization. So any transverse wave can be polarized. You can't polarize a longitudinal wave. So what polarization means, if you remember with a transverse wave, that's our direction of wave propagation. Everything that's oscillating is oscillating at 90 degrees to the direction of wave propagation. Now, if you were looking at this propagation coming out of the screen, so that dot is like an arrow coming straight at you out the screen, the oscillation could be up and down, it could be an angle, it could be side to side. We've got all of these different directions that the oscillator could be moving in. Now, if the wave is polarized, it will only be moving in one direction. It might be up and down, it might be at an angle or whatever, but it's polarized in a particular direction. You've got all of the oscillation happening in that direction. And this can occur naturally in some cases. Quite often when you get reflections happening, you can get polarization, or at least part polarization of a wave. But sometimes it's really, really useful to set up plane polarized waves, because if you've got one wave which is oscillating up and down and the other one which is oscillating, another wave which is oscillating left and right, and they overlap, they're not going to interfere with each other in such a destructive way, because their displacements are off to the they're at 90 degrees to each other. If we've got everything's oscillating up and down and they superpose, and one of them's got amplitude plus amplitude, the other one's got the negative amplitude, they're just going to destructively interfere. But you don't get any of that going on if they are in perpendicular polarizations. So quite often you'll see in transmitters and aerials, you'll have some of them that are vertical, some of them which are horizontal. So they can be set up near to each other and not interfere. So that is particularly useful. And aerials are quite interesting in themselves, in that, I mean, a transmitter and a receiver are quite similar in the setup. Yeah, you've got a vertical aerial, you're just setting up this conductor, really. You've got this bit of wire. Okay, it can be fairly thick wire, and you're setting up an electromagnetic wave, like a standing wave in this wire. But you can then control it. If you shut it down, if you collapse that wave by turning off the thing that's creating it, then you get this coordinated disturbance then propagates out into space. And if that's then picked up by a receiver, which is also just a conductor which is aligned with this, then as the wave comes in, it then creates an electromagnetic wave which can then be interpreted. So it's just a way of passing this information from one conductor to another. And these are plane polarized, which is really, really useful, because you can set up another one which is horizontal, which has got all the horizontal waves going across in the same space, and they're not bothering each other. And these can get really fancy as well in how they set up the waves. Usually you're going to get a combination of different waves combined together. So you'll get a carrier wave, which is just sort of base sine wave, which might be going along something like that. And then you can modify that in different ways. So this wave will be set up in a regular fashion. You might have some quartz crystal oscillator, something a bit like you'd have running a clock or something, which is setting up this very, very regular standing wave, which you can then, base wave, which you can then modulate. Right, you might change the amplitude of this in some way, or more commonly nowadays, you get frequency modulation. So you can get what's called frequency shift keying, where you switch the frequency of this wave between, you flick them backwards and forwards between two different frequencies, which are representing 0 and 1. So you're passing binary information across. So you're taking this base wave, but then you might have some high frequency. You don't change the amplitude, so you might go high frequency for a couple of cycles, then you might go lower frequency, and then back to high frequency again. So you're keeping the amplitude the same, and then you're modifying the frequency or the wavelength, same thing. But you've got frequency modulation is then your FM on your FM radio on this frequency shift, frequency shift keying, if I can say it right. And it's better to modify the frequency if you can, because that gets affected less during transmission. There are a lot of things, the attenuation of the wave, a lot of the losses that you're going to be getting, that affects amplitude, but it won't affect frequency as much. So it's a lot easier or more accurate to then decode the frequency at the receiver than it is to decode amplitude. So that's why you get better signal on FM radio. So trying to think, oh yeah, there's one other thing I suppose on that is to then talk about, we got Malice's law. So you get Malice's law with we use polarizing filters quite a lot, and this is one of the experiments that comes up in A-level physics, but these are the sort of filters you get on sunglasses. Yeah, as I was saying, if you get reflection off of water of light, it gets you get plain polarized light. You can then cut the glare on the light by wearing sunglasses, because you've got a polarizing filter which is only allowing certain directions of oscillation of light through. So it's like you've got this, you could think of it almost like a grid where you're only allowing things which are oscillating up and down to go through the gaps on the grid, and everything else is getting stopped. So that's how you can think of these filters. I mean, in some cases with electromagnetic waves, like with microwaves, you literally can set up metal grids that will both polarize microwaves and block incoming polarized microwaves. They are, it's literally, you can set up like square chicken wire sort of thing in order to do it. It's a much finer effect if you've got visible light and sunglasses. But you've got these polarizing filters which are useful for something like that because it cuts out a lot of the glare. But if you've got this, essentially this grid where you're allowing vertical oscillations to go through, well, this will be any vertical component of the incoming light. So if you've got some light which is oscillating off at an angle, we can then take the vertical component of that in the usual sort of vector fashion, just taking multiplying by the cosine of the angle. And then that is the component which will then transmit through the gap, which is why you get this weird effect that if you set up one, well, it seems weird when you first come across it. If you set up one vertical polarizing filter and then behind it you set up a horizontal one, so some light comes in through the first one, but once it's gone through the first filter, all the oscillations are going to be up and down because that was the only set of components that were allowed through. So then when those up and down ones hit the horizontal filter, you're going to have nothing go through. So everything's just gone completely black when you've got them perpendicular to each other. But if you put a third filter in between, which is at say 45 degrees, then all of a sudden you start seeing light going all the way through, and you think, well, how can this be the case? How can you put another blocker in between and now we're seeing things again? And it's because we're doing these components. You go through the first one, we've now got everything up and down. You hit the second one, well, we now get all the components which are going at 45 degrees from vertical. Then you hit the third one, and now, we got another set of components which are going to be the components which are going horizontally. Okay, they're reducing down each time because we keep multiplying by cos theta every time we go through another filter, but it's still giving us a component that's going to pass through this cascade of different filters. And this is what's going on then with Malice's law, because we can see that just from doing, this is looking at the amplitude of the oscillation. So our amplitude when we pass through a polarizing filter is going to go from initial amplitude A to an A cos theta. And we're going to get this every time we're going through these filters. We're going to get a cos theta thrown in every time. And that is the change in amplitude. And of course, our intensity is proportional to amplitude squared. So the intensity is going to be equal to the intensity times the square of cos theta, because we're going to say, well, amplitude squared is amplitude squared times cos squared, and then we're replacing the amplitude squareds with intensities. So this is then what we're getting with Malice's law, where we can say as we're passing through these filters, this is the change in intensity that we're going to be getting based upon the direction of the oscillation and the orientation of the polarizing filter. What is the angle between the oscillation and the filter? and that is then the relationship in the intensity. So yeah, that's a particularly useful one that we will be using quite a lot in exam questions, because it can be quite difficult to describe this setup of the three polarizing filters. Essentially, the verbal description of Malice's law can be quite difficult to do in an exam question answer, but they allow you to talk about it in a mathematical way. So I'll be doing this in a lot of the practice exam questions that I'll be running through in videos in a few weeks' time. I think that's covered everything, or if it hasn't, I've just forgotten about it. So I'll just leave it there. That's 2 videos covering the high spots of electromagnetic waves. But just to underline those last 2 bits, coherence, that applies to any wave, not just electromagnetic waves and not just transverse waves. You can talk about sound waves being coherent and they're longitudinal. And polarization, that can apply to any transverse wave. So although we're talking about them in our particular case study of electromagnetic waves, they are by no means specific just to electromagnetic waves. It just happens to be what we're talking about at the moment. So there you go. That's wrapped up those.